for you to see a pattern. It's not enough for you to see that it's increasing or decreasing. So we need another way of doing it other than visually, all right? So pay attention, this is super important right now, all right? I'm going to show that this is eventually increasing. And this is the way I'm going to do it. I want to show, now I'm not going to write want to show anymore because it's a pain in the ass. I'm going to write WTS from here on out. I would like to show you that this is increasing, okay? I would like to show you A sub n is increasing. Eventually, yeah, eventually. So, I want to show, what does it mean to be increasing? That A sub n is smaller than A sub n plus 1, right? That's the definition of increasing, is that this one is smaller than the next one, right? I need to convince you that this is true. So tell me, what is A sub n? Well, that's the original formula, isn't it? The original formula is 10n over 2n plus 1. I want to show you that that is smaller than what? A sub n plus 1, which is that formula with n plus 1 plugged in, right? So let's take that formula and plug in n plus 1. And be real careful, because that n plus 1, wherever you put it, you're going to have to distribute things through. See, I'm trying to convince you that this is an increasing sequence. I'm trying to convince you that it's increasing. So what I'm doing is I'm going to try and convince you that this inequality is true, which means that I have to prove to you that this is true, right? Right now, I don't know if this is true or not, okay? I don't know if this is true. I hope it is, and I hope I can convince you that this is true. With me? So now what I'm going to do is just some algebra, all right? Let's go ahead and distribute the 10 through here, distribute the 2, and collect things together. We should get 10n over 2n plus 1 smaller than 10n plus 10 over 2n plus 3. Y'all know what I did there? Right? 2n, 2, add the 1, you get 2n plus 3. See, this is still a question. Is this true or not? If I can convince you that this is true, then I think you'll be happy, right? If I can convince you that this is true? Yeah, let's clear fractions. In other words, I'm going to multiply this side by the 2n plus 3. I'm going to multiply it here and here. And then I'm going to multiply 2n plus 1 here and here. So what's going to happen is, y'all have heard of cross multiply before? I hate that term. That's technically what I'm doing here. Well, no, technically I'm clearing the fractions, but you can look at it as cross multiplication. So I'm multiplying 10n by 2n plus 3, and that's less than 10n plus 10 times 2n plus 1. Hey, wait a minute, hold on a second. We have an inequality. Don't we have to worry with inequalities that when you multiply, sometimes the inequality flips? When does it flip? When you do what? When you divide or multiply by a negative number. So when I cleared the fractions here, was that ever a negative number? No, because 2n plus 1 would always be positive, right? Because n is either going to be 1, 2, 3, 4, 5, right? So this will never be negative, and that'll never be negative with the restriction, right? Because we're talking about a sequence. So I can do this clearing of fractions without flipping anything over. But I still don't know if this is true, right? So now let's multiply this out. This is 20n squared plus 30n. Is that less than or equal to, okay, here's a little harder. 20n squared, and then I'll have 10n and 20n, that's 30n, and then plus 20. Y'all good with that? What happened? Oh, 10, yes, thank you. I don't know where I got that 20 from. Thank you. Yeah, do y'all see you can just start subtracting things? Look, I can subtract 20n squared, subtract 20n squared. They go away. I can subtract 30n. I can subtract 30n. They go away. And what am I left with? 0 is less than 10. That's true. I started with this expression and said, hey, I'm not quite sure this is true or not, right? This may or may not be true. I can't just tell by looking at this that this is true. But when I work through the algebra, I get to this statement at the end, and that I do know is true, right? 0 is less than 10. So if this is true, that means this is true, which means it's increasing. Got me? I'm done then. That's all I need to do. So on your homework, you'll be given a sequence and you'll be asked to show if it's increasing or decreasing. That's what you have to do. You don't list out the numbers and go, yeah, it looks like it's getting bigger. Or look, you have to do that. All right, let's move on. Bounded sequences. A sequence is said to be bounded above. Bounded above. If there exists a capital M such that a sub n is smaller than or equal to capital M for all n. And then a sequence is said to be bounded below if there's a little m such that the sequence is always bigger than or equal to that little m for all n. All this is saying is that your sequences are stuck either under a number or above a number. So look at this blue sequence right here. We would say that that sequence there is bounded above because there's some number it never reaches. Okay, so it's like a ceiling and the sequence never goes above that ceiling. That you would say is a function that's bounded above. If you have a floor that your sequence never gets to, you would say it's bounded below. That make sense? In either case, all right, so I'll take that back. Let's look at this one, sorry. Look at that, that was that sine one we looked at earlier, right? Sine n, that is a bounded sequence. This is both bounded above and below, right? So I need to go back up to the definition because I skipped over that last part real quickly. Right here. Bounded above just means you have a ceiling. Bounded below means you have a floor. If a sequence is bounded above and below, we call it bounded. So if you have a ceiling and a floor, you are looking at a bounded sequence. Just a ceiling is called bounded above. Just a floor, it's called bounded below. Both together, bounded. All right? So that sequence we looked at earlier, the sine n, that is a bounded sequence because it's got a ceiling and a floor. Now why is this important? This theorem right here. Oh, I forgot to say something else. Where is it? It's not in the definition? Oops. I forgot this when we talked about increasing and decreasing. My apologies. Increasing, we said it goes up. Decreasing, said it went down, right? In either case, the sequence is called monotonic. Monotonic. So if you have a sequence that goes up, we call that a monotonic sequence. If it goes down, we call it monotonic. So monotonic is kind of general. If you just say a sequence is monotonic, you're not telling me if it goes up or down. You're just telling me it goes up or it goes down. Right? So monotonic is kind of general. Then you have the idea of bounded, which is a ceiling and a floor. And that allows us to have a theorem. This theorem says every bounded monotonic sequence converges. Every bounded monotonic sequence converges. Does that make sense to you that that would be true? Every bounded monotonic sequence converges. So let's say that I have a sequence, right? I have some sequence. I'm going to draw you a sequence, all right? First thing is I'm going to say it's bounded, okay? Bounded. So assume I have a sequence that's bounded. That means it has a ceiling and a floor, right? So I've got some ceiling. It never goes past that. I've got some floor. It never goes below that, little m, okay? That's a bounded sequence. So I'm going to start drawing my dots, and I've got to stay between these two lines, right? But the next condition is that it is monotonic, which means that as I draw my dots, they either need to keep going up or they need to go down. So let me just make it go up. So let's say my first dot's here. My next one has to be above that, right? Yeah. And then next one's got to be above that, above that, above that. Do you see that there's no way, I have no choice but to converge to something? I have to converge. I can't oscillate because monotonic means I need to keep going up. And then the ceiling means I can't just keep going up forever, right? So I've got to head to somewhere. So somewhere in here I have an L, a limit that I'm going to approach. Now it might be M, okay? M might be the limit, okay? But no matter what, there is a limit. And that's what this theorem says. Which means that if you ever have a sequence and you're trying to show that it converges to something, then all you really have to do is show, one, that it's bounded, and two, that it's monotonic. And if you can show me that, then you can prove that it converges. I'm trying to figure out which one I want to do here. Let's do that one. I'm giving you a sequence here. Square root of 2. Next, square root of 2 square root of 2. And then the next one is square root of 2 square root of 2 square root of 2. The next one would be, they didn't list it, square root of 2 square root of 2 square root of 2 square root of 2, and so on and so forth. Does this converge? Does it diverge? Find the limit of the sequence. Not obvious, no? Not obvious? Well, it would be useful if we had a formula, right? If we had the formula that generated this sequence, that might be useful. Because then we could take the limit and let n go to infinity, couldn't we? But we need the actual formula for the sequence. So do y'all think we can come up with a formula for this? How could I rewrite this? 2 to the half, right? This is 2 to the half power. All right? How could I rewrite this without using radicals?
2 to the half times 2 to the quarter.
So you would have, okay, let's do it this way. We have the whole thing to the half, right? That's this square root, right? And then you have 2 times, and then this would be 2 to the half again, wouldn't it? So this first one is this, but that's 2 to the half. Let me do this one. What would 2 times 2 to the half be? What do you do with their powers? You add them. So this is 2 to the 3 halves. Yes? 1 plus a half is 3 halves. So 2 to the 3 halves. But that's raised to the half, right? And that's 2 to a power to a power. What do you do those? Multiply, right? So what's 3 halves times a half? 3/4, right? So we have 2 to the half, and then this is 2 to the 3/4. With me? Yeah. Let's try and get this one. This would be half power here, right? And then 2 times what? Another. This is getting complicated, yeah? But do y'all see that this right here is just this? And we know that that's this. Right? All that work, we know that that's this, right? So this is really 2 to the 3/4, right? 3/4? And now let's put 2 to the first power times 2 to the 3/4, which would be 2 to what power? 7/4. And then we still have to raise that to the half. So that'd be 2 to the what? 7/8. You'll follow that? That's kind of cool, huh? All right, let's keep going. This one would be all this to the half, right? This 2 here, and then again, same exact thing we just did. Everything here, right? Root 2, root 2, root 2. All that is this one, right? That's this right here, which we said was this. So this is times 2 to the 7/8. And what's this? When we add those together, we have to do 1 plus 7/8. That's 15/8. 2 to the 15/8 raised to the half again. So this final one would be 2 to the 15/16. Questions? Do you have a guess as to the next one? Do y'all see a pattern here? What's the pattern? Do y'all see, who sees the pattern?
The numerator or the denominator is going to double it this time.
Okay, so the denominators are just powers of 2. 2 to the first power, 2 squared, 2 cubed, 2 to the fourth, right? And what about the numerators?
It's 2 cubed minus 1.
It's-
Or 2 to the power of n minus 1.
Exactly, it's just 1 less than the denominators, right? This is a 2, that's a 1, that's a 4, that's a 3, that's an 8, that's a 7, that's a 16, that's a 15. So it's just 1 less than whatever the bottom is. So what would the next one be? Just so we have it, 2 to the what? 31 over 32. Next one, 2 to the 63 over 64, right? So I think I'm ready for the formula. A sub n should be 2 raised to the, let's do it this way. The bottom we know is 2 to the n, is that right? Would that work for our first one? That would give us the 2 down here. And the next one would be 2 squared 4, right? That's the bottom. And then what about the top? It's that minus 1, right? 2 to the n, take away 1. That's what we have, right? All right, I would like to know what happens to that as n goes to infinity. Right?
Power approaches 1.
This approaches 1? How do you convince yourself of that? I'm going to help us do it. Ready? Watch. Does anyone have a question on where that came from? Are you sure? So what I'd like to know is what is the limit as n goes to infinity of 2 raised to the 2n minus 1 over 2 to the n. 2 to the n minus 1 over 2 to the n. Right? I want to know what that limit is. Now, this can be rewritten. I think this is the key to the problem here, to this part, is to rewrite that as 1 minus 1 over 2 to the n. Look, you have 2 terms in the numerator, right? 2 terms in the numerator, 1 term in the denominator. So split it into 2. Do this over this, which would be 1, minus that over that. Got it? With me? With me? Now this, I want you all to look at that as being 1/2 to the n. Isn't that the same thing? Right? And now, right there. Do we have r to the n? Is r smaller than 1? What does this go to? 0. So that, when I take this limit, that goes to 0, which leaves me with 2 to the first power, which is 2. The sequence converges to 2. So if you do that, right, 2 root 2, and the next one 2 root 2 root 2, and then 2 root 2 root 2 root 2, and you keep doing that forever and ever, those answers are going to get closer and closer and closer to the number 2. Weird, right? Okay, I think we have laid the framework for everything. I do want to mention one last thing. When you go do your homework, you're going to be doing, like, they're going to be asking you to find what these sequences do. There's not going to be an example like things I've done in class for every single one of these, all right? You're going to have to draw back on some of your Cal 1 knowledge. I just want you to know that as you get to this homework, be aware of that. Like here, yeah, I mean, just be aware of that, all right? But there's one last thing here. Not all sequences are defined with a formula, okay? Not every sequence that we have out there has a formula to it. There's another type of sequences that we're not going to get into in this class called recursive sequences. And the most famous one is this one here. I'm going to put the sequence up, and then I'm sure someone here has seen it before. I'd be shocked if you haven't. The sequence 1, 1, 2, 3, 5, 8, 13, 21. I would be shocked if somebody hasn't seen it. I'm not shocked if everyone hasn't, just I know somebody's seen that sequence before. No? No? Huh, I am shocked. You haven't seen it? Okay, good. If you haven't seen it, this is a really cool sequence. I'll tell you that there's not a formula for this that's easy. All right? There's not an easy formula for this sequence. But there is a way we can define it that is very easy, and it's tied in this idea of what we call a recursive sequence. So does anyone see the pattern in it? Kind of tough pattern to see. Can anyone predict the next number?
It's the last one times, or that last one added together and the one before that multiplied. Like,
What would the next number be? Let's start with that.
two numbers before that.
So what would it? 34? That is the next number. Where did that come from? You add those two together. So a number in this sequence is the sum of the two before it. But that pattern only starts right there. So you start with two ones. Now your next number will be, this number right here is those two added together. That's 2, right? Your next number are those two added together. That's 3. Your next number are those two added together. That's 5. Your next number is those two, 8. Next number, those two. Got it? Y'all haven't seen this before? I might misspell this. Fibonacci sequence?
That's the name that came to mind. I didn't.
Yeah, the Fibonacci sequence. So how do we define this, right? How do we define this? We use what's called the recursive definition. So watch me write it down first, and then maybe it'll make sense. First thing I'm going to do is this. I'm going to write down let a sub 1 be equal to 1, and let a sub 2 be equal to 1. So I'm telling you, I'm giving you the definition of the first two numbers in the sequence. All right? Now I'm going to define what every other number in the sequence must look like. A sub n will be a sub n minus 1 plus a sub n minus 2 for all n's greater than or equal to 3. That is what we call the recursive definition. So what I'm saying to you, for example, let's say I wanted to know, let me just show you how this works. Let's say I wanted to know what the sixth number in the list is. 1, 2, 3, 4, 5, 6, right? I want to know what that number is. What it will be according to this formula is a sub what? If I want to know what a sub 6 is, it's a sub 5 plus a sub 4, right? It's the sum of the two before it. Make sense? The bad thing about this formula is that now if I wanted to know what a sub 5 was, what's a sub 5? What's a sub 5? It's a sub 4 plus a sub 3, right? But what's a sub 4? A sub 3 plus a sub 2. Okay, what's a sub 4? A sub 3 plus a sub 2. And you have to go back until you get back to the two numbers that you do know. In other words, in order to find the 100th term in the sequence, right? The 100th number, you have to know all the ones leading up to it. It's not like it's not like these formulas. Like if I gave you a sub n is 2 to the n over 5n, I could very easily ask you, hey, what's the 10th number, right? You just plug in 10, you're done. With recursives, it's not so simple. But it's a nice way to create sequences. How are we doing? I only have 8 minutes. Okay. Since I've got it on the board, where's the Fibonacci sequence come into play? May as well show this to you. I'm not going to test you on recursive sequences at all. And there's nothing special about the Fibonacci. You know how we started with a sub 1 is 1, a sub 2 is 1? You could have said, let's let a sub 1 be 4, and let's let this be negative 5. And then you could have said that from here on out, the next number is twice this number minus 5 times that number. You could do anything you want. Fibonacci is just 1, 1, and then the next one just add the previous two. That's Fibonacci. But really, it could be anything you really ever want it to be. Here's why Fibonacci is interesting. Because if you look at the sequence, if we start here, I'm going to draw a box, okay? A square. That's a square. And I'm going to tell you what the area of that square is. All right? So this side right here, I'm going to tell you is 1 by 1. That's a 1 by 1 square. So I'm going to put a 1 inside. That 1 is the area. Got it? Sorry, hold on. That's not what I want. I apologize. That's the 1 is not the area. The 1 is the length of the side. Sorry. It's how long this side is. It's not the area. It's this is 1 by 1 by 1 by 1. Okay? I'm going to draw next to it another square. Like that. What number goes inside there? If I tell you that is a square, what number should go in there? 1, right? Because the length of the side should be 1, 1, 1. Now I'm going to draw another square. What number should go in there? Not the area. See, I already messed you up. The number goes in there is the length of the side.
2.
So that should be a 2, right? Because this is 1 and that's 1. And now I'm going to do this one. And I'm telling you, this is a square, okay? That's a square. What's the number in there? 3. Okay, and then I'm going to draw another one right here. What number goes in there? 5, right? 1, 1, 3, 5. Let's do another one. What number goes in there? 8. Okay, 1, 1, 2, 3, 5, 8. Do you see it? Okay, I'm going to do one more. It's going to be too big here. But what goes in there? 13. Okay, so now we've got this weird shape, right? We're going to start with the first box, the top corner right here. And we're going to draw, to the opposite side of that box, we're going to draw an arc. And then from that corner, we're going to go to the opposite corner, continuing the arc. And then from that corner to the opposite corner, continuing the arc. And then you continue this arc through and through like this. And you get what spiral? You know what it's called? No? The golden spiral. The golden spiral. The golden spiral. So we believe that think about like if you've ever looked at a seashell, right? Like if you ever looked at a little shell and you kind of look at them from the side and you see the little shell, you can see the spiral of the shell. When you think about a spiral, you could have a spiral that does something like this. Not a very good picture, but do y'all see what the spiral I just drew? That the distance between the lines is the same the whole time? That's a spiral, right? That's not what a seashell looks like though, right? A seashell the spiral starts real tight and then it kind of spreads out as it goes, right? That's what a seashell does. In nature, we believe that the spiral that we see in nature like this is this spiral. The ratios are correct. The way the spiral grows, like the gaps between the spirals are getting bigger as you go out. That's what's happening here. It's real tight in the beginning, but as you draw this bigger, the gaps get bigger. And we can't really explain why it's like that, but it is. So that's why this sequence gets such, what's the word I'm looking for? A lot of people look at this. The Greeks looked at this. They believed that this created a perfect ratio, all right? So like if we keep on going and keep on going forever, if you take this number divided by this number, and you keep doing that, so you take that divided by that, other way around, this one divided by this, and you do that, this one divided by this one divided by this, that creates a sequence of numbers that converges to a number which we call the golden ratio. And so the Greeks, when they were building things, they would always use that ratio, that perfect width to height dimension. When they did buildings and windows, and that's what they did. So anyway, it goes back, historically it has a lot of significance, the Fibonacci numbers. Let's see, so recursive sequences, all I have here is, yeah, so I just put here in the notes the Fibonacci sequence. So at this point, what I would expect for you to do for homework is finish up the 8.1. Okay, so now go ahead and look at those problems 5 through 32, right? Wait a minute. Yeah, right here. 5 through 32, 37 through 40. Look at those problems. And I was asked earlier, where should you turn those in online? Turn them into the 8.1. If not, you can turn them into the next one, the 8.2. It doesn't matter where you turn it in. And then next time, we're going to start 8.2 series, all right? So we've done sequences. We've got all the groundworks in place, and now we actually start looking at what a series is. Now, before you go, because I still have you for a minute. It's Halloween, right? You can start packing up, just, you know. Real quick idea. What is a series, right? What's the difference between a sequence and a series? Yeah, a sequence, okay, what we just studied is just a list of numbers. So let's say a half plus a fourth plus an eighth plus a 16th plus a 32nd. That's an example of a sequence, right? It's just a list of numbers. All a series is just add those up. That's all it is. So take